Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we discuss a concept regarding the force exerted by the jet on a stationary curve plate. So previously already have discussed regarding the force exerted by the jet on a stationary flat plate like vertical plate and the inclined plate. Now we are going to discuss about the curve plate. So in this force exerted by the jet on a stationary curve plate, it is also categorized into three types. So first category is or first condition is we can write the jet strikes the curve plate. So first category is the jet strikes the jet strikes the curve plate the curved plate, as you can see the diagram, at the center. Curve plate at the center. You can see the jet is striking the curve plate at the center of this plate, and this is one category. Second category will be like the jet. Here I can write this is the jet strikes the curve plate, okay, at one end at one end tangentially when the plate is when plate is symmetrical when plate is symmetrical. This is second condition. And the third condition is the same jet strikes the curve plate. Here we can write more at one end tangentially at any one. This is one end and this is another one. At any one end, the jet strikes this curve plate tangentially, and here the plate we need to consider unsymmetrical. We can write here this is unsymmetrical. So these are the three categories are there. So out of these three category, today we will discuss about the first one. So that is nothing but the jet strikes here, right? The jet strikes the curve plate. The jet strikes the curved plate at the center. Curved plate at the center. So for this we have taken this diagram from the book, and here we'll discuss one by one. So first of all, we need to consider that a jet of water, suppose this is the pipe through which the water is flowing, and to this pipe one nozzle is fitted to this one, and this is the jet of water which is coming out from this nozzle, and suppose this one we can write this is jet. So this is the jet of water, yeah, and this is the plate what we can see. This is the curved fixed plate. This is the fixing symbol is there. You can see this symbol is given for fixed, or you can say the plate is stationary, okay, and this is the plate actually. The hatching line you can see, this is the plate, okay, curved plate actually. This is the curved plate, okay, and this is the jet of water which is coming out from the nozzle, okay. After striking this jet of water on this curved plate, the water again it's moving with the direction, with the curved plate direction, how it is you can see here. So the velocity of water which is coming here after striking in the curved plate, it is moving in this direction, and we can see this is the velocity of water is coming out from here. So okay, so where we started, like let consider the jet of water strikes a fixed curve plate at the center. So this is the center point. Let's see, this is the this is the axis line of this, and it is striking the fixed plate at the center. Now after striking the plate, the fluid which is coming out from this plate with the same velocity, okay, the fluid will come out from this plate with the same velocity. Initially, what is the velocity is here? That is V. So initial velocity of this jet is V. So we'll consider some parameters here, like V equal to velocity of the jet. So few things we can consider directly. I'll just write shortcut of this. V equal to velocity of the jet. Similarly, we can consider D. D is nothing but diameter of the jet. Dia of here jet we can write. So unit we can write this is meter per second, and dia here we can write this is meter. Similarly, area, if we want to calculate of this, we can calculate the cross-sectional area, of the jet, and that one we can calculate meter square. This is nothing but pi by 4. This is d square. And similarly, the fluid is moving, so we can calculate the mass flow rate of this. So mass flow rate already we have calculated in the previous two lectures also. Here also if required we'll calculate. Okay. Now the velocity of jet which is striking this curved plate, initially it is moving with the velocity v. Now the velocity of this jet will come out from this plate, okay, with the same velocity it will come out. When it will come out? When the plate will be in smooth condition. When the plate is smooth condition, then we can consider that there is no loss of energy. No loss of energy. No loss of energy. So due to the impact of jet. Okay. So the velocity in the tangential direction from the curved plate, we can get it at the outside like a V. Okay. So now if you see this diagram, now this is the fluid velocity, jet velocity is there, and this is the curved plate, suppose. Okay. Now through this curved plate, if you see, the velocity also coming out from this, and the velocity also coming out from this, both side. Okay. Now if I consider this velocity v at the outside, okay, and what is the angle of between this fluid velocity and the angle of coming out, the fluid which is coming out from this plate, what is the angle between this? So if I draw this velocity of this to this, like this fluid direction, actually this is the fluid direction, or you can say this is x direction, the direction of jet. Okay. So if I consider, so this angle will be like theta angle will be there. Okay. Similarly, this side angle will be considered, that is 180 minus theta. This is actually angle of deflection, we used to call. This is angle of deflection, and this is the angle between the jet of fluid and the fluid which is coming out from the plate. So that is V. Now, though you can see this velocity is coming out from this plate with some angle, then we can resolve this velocity in two components. So the velocity at the outlet condition, this is at the outlet condition. So this velocity can be resolved in two components. One is this y component, another one is x component. Okay. So this angle you can see here. So we can write this is theta here. Okay. So now we know that how to resolve this one, and this is theta. If I draw here like this, then this will be our, like, base will be there, and this is perpendicular, this is hypotenuse. So this one you can resolve, and we will get this is V cos theta, and this is V sin theta. This is V cos theta, and this is V sin theta. Now the component of velocity in the direction of jet, in the direction of jet means in this direction. In the direction of jet means in this direction. We can see the jet is moving in this direction. So first we can find out the component of velocity in the direction of jet is nothing but V cos theta. But we can see the jet is moving in this direction, and here the component of velocity we are getting in reverse direction. So here we will get minus V cos theta. This is minus V cos theta, and this is V sin theta. So this is in x direction, this is in y direction. So initial component of velocity at the inlet condition, you can see this is Vx, this is Vx, okay, or V1x, and this one we can consider this is V2x, final component of velocity in the x direction. Similarly, at this condition, if you see, this is V1x as I have written here, one direction in this x direction. Similarly, in the y direction, this will be v1y, velocity in the y direction. Similarly here we can write this is v2y, okay, final velocity in the y directions. So now we can write the component of velocity in the in the direction of z, that is minus v cos theta. So let's find out now what is our main intention. We need to find out the force exerted by the jet on the stationary curved plate. So these things we can identify from our Newton's second law of motion, that we know that Fx is equal to nothing but the rate of change of momentum in the direction of x, or we can write this is in other terms also we can write this is like mass into acceleration. In this form we can write, or we can write the rate of change of momentum also we can write in that way. So if you write in this way, then we can write this is mass into acceleration equal to change in velocity by change in time. And this one again we can write change in velocity is nothing but we can write this is v1 minus v2, initial velocity minus final velocity. And here also change in time is nothing but what is the initial time and what is the final time. So this one I'll just write in terms of, after differentiating we can write in time only, okay. And this one mass per time, or in place of mass we can write this we know that again rho equal to mass by volume and mass equal to rho into v. So here I can write this is rho v by time, rho v by time. So this is volume by time. So volume by time, and this is velocity difference. Now volume by time we can write this is volume by time, that one you can write in terms of unit meter cube per second, which is nothing but discharge or Q. Okay, Q is also same thing. What is the amount of water is coming out with respect to time. So this one we can write rho Q and v1 minus v2. Similarly again we can write this equation. Yeah, let's write this is fx we can write mass flow rate, mass per second, this one rho Q, or I can write this is directly I can write rho a v. So Q equal to, we know that AV, area into velocity. So we can write rho AV into change in velocity, like v1 minus v2. So that is nothing but v1x minus v2x, because we are calculating the force in the direction of x or in the z direction. So here we have already found what is the v1x. V1x is nothing but this one velocity v, initial velocity, as I told you here, initial velocity, that is v. So what I'll write here, rho a v multiply v1x, that is nothing but v, minus what about the v2x. V2x we already found here, this one v2x minus v cos theta. So minus this is plus, so this is v cos theta. Now here if I take common of v and I'll put it outside, so we can write this is rho a v square, and here bracket will be start plus 1 plus cos theta, 1 plus cos theta, and this one we can give equation, yeah, this one you can give equation 1. Okay, so this is the force exerted by the jet on the curve plate in the x direction, in the direction of jet we can say. So this is one part. Similarly we can calculate the Fy. Similarly we can calculate the value of Fy. So Fy is nothing but, again we can write the same thing, like the force exerted by the jet in the y direction. So similarly Fy also you can write the mass flow rate, or you can write the mass per second. This one also you can write, this is mass per second into v1y minus v2y. Okay, v1y minus v2y. So v1y is nothing but initial velocity in the direction of y. Okay, so what about the v1y and what about the v2y, we need to identify. So v2y already we have calculated here, you can see this is v2y, this is nothing but v sin theta. Okay, and what about the v1y? V1y, as I told you, initially the fluid is moving in this direction. Here we can see the fluid is moving in this direction of z, that is only x direction. So there is no movement in the y direction. After striking, it moved in the inclined direction, so that we have made these two components, x and y direction. But initial velocity in the y direction, that is 0, as we got previously, like v1x is nothing but v, and v2x and final velocity. After striking, you can see if it is stopped here or if it is moved in the vertically upward direction, then it is different. So velocity will be, final velocity can be considered as 0. But here the velocity came out from this plate with an inclination. You can see this velocity. That's why, okay, this velocity, that x velocity, if it is in the x direction, means it should be moved in this direction. But here you can see the velocity moved in the opposite direction. That's why we have taken this one. This is f2x, final velocity in the y x direction, minus reverse of this one. Okay, that's why I have written this one v2x here. Similarly, v2y is v sine theta, and v1y equal to 0. Just put the value here in this equation. So we can write fy equal to, again, this mass flow rate for second, mass per second, we can write this is rho av, and here we can write this is v1y is 0 minus v2y is v sine theta, bracket close. Now here again we can write this minus term, we can take it to the outside here. So we'll get minus rho av. Yeah, v we can square here, and this is sine theta. This is another one equation we can mark here, equation number 2. And this is the second equation, the force in the y component, and this is the force in the x component. Okay, so this is the two equation what we got here in the x and y component. And now you can see we got the value here minus negative term is there. So this negative sign indicates that the force acting in the downward direction. The force acting in the downward direction. That means here x direction we can get the force in this, and y direction will get the force in the downward direction. So for this, in this case, the angle of deflection we need to consider, that is 180 minus theta. So the force in the downward direction here you can see, and for this case we need to consider the angle of deflection, the angle of deflection of the jet. Angle of deflection of the jet is nothing but 180 degree minus theta. Okay, this is theta in this direction, and theta is angle of deflection. I hope you understand this concept of force exerted by the jet on a stationary curved plate. So the first one we have completed in this lecture, this point we can see. Remaining two is there when the plate is symmetrical, when the plate is unsymmetrical, and when it is acting on the one end of the tangential. So this is one end of the plate, and it should be strikes to this tangential directions, and when the plate is unsymmetrical, third one. So I hope you understand this lecture. Still, if you are having any kind of doubt and query regarding this, you can give a comment on the comment box. Thank you all.